So now we're recording, the subtitles are on. Thank you. So today we will try to go into concrete as a material. We'll try to see it in one single lecture, because on Friday, I want to have this kind of a material samples experience workshop, so we can see the stones and the bricks and the tiles, and hopefully some metals. It is very hard to make it here, so probably we'll do it outside in the lobby, in the stairs. So we can move around. It's much more easy to do by groups. So it's about 50 students, so probably we make groups of 5 or 6 for each set of materials, right? And we see it. Other thing, I'm trying to adjust a little bit the lecture plan to fit on time, because we slowed down a little bit. So probably Friday, I'm not sure we have time for a lecture. We will see, after concrete, we will see glass, which is the last inorganic material, and actually it's, again, one processed stone. And then we're going to timber, right? I will try to have at least timber before the midterm. Timber is longer, more interesting, but more difficult. That said, still on Friday, please have your assignment ready. I see some students missing classes, missing quizzes, and missing assignments. Please, we had too many things to have many possibilities where to get your points and to pass the course. If you start missing everything, it will be very hard to recover afterwards. So concrete is quite interesting material. Actually, in the world, most consumed material is water. Second one is concrete. So much we use. This is a photo of one of the handrails of the Seun Sanga before the renovations, which is already old concrete. We'll have, as usual, some historical outline. Then we will concentrate on the material, and finally we'll see some environmental issues. Right. So, as we did with the metals, we will have a few, not just the timeline, but some thematic issues like a mass, skeleton, engineering sculpture, texture, shell, and prefabrication. Massive concrete we have remained since the Romans. Let's say like 2,000 years ago. And this demonstrates the versatility and the durability of this material. Okay, so basically it's the same material. Modern concrete actually started to be used end of the 19th century, 20th century. And the first project trying to use those plastics possibilities of the concrete was Erik Mendelsohn, great architect, the Einstein Tower in Potsdam. Ironically, technology was impossible at the time, and they had to build it on brick and then render on cement. So the most influential concrete building is made of bricks, which also says something in favor of bricks. It is engineers who really started to figure out how to use this material and who developed all the mathematics we use today to calculate. Maillard was one of them, Swiss engineer, and his bridges became famous, and actually they are still in use. Something we learned very fast is that concrete, as it has been poured and formed, creating that form was as much a challenge as the structure itself. So whenever you have some kind of interesting in concrete or unique, the auxiliary structure is usually as much as a difficult engineering as the concrete itself. And this also a limitation of this kind of material. We have to go to the early 20th century together to Mendelssohn, Auguste Perret, which was the master of Le Corbusier, was one of the first to use concrete seriously, which was kind of engineers for factories, bridges, and he did something unbelievable. He made a big church on concrete in France. That was a scandal, but as it happens often in France, that scandal becomes kind of an advancement in science and art. And then became like a normal material. We have Le Corbusier, domino system, and the normal skeleton construction. One milestone is 1965. We have a SOM, This Khan is not the architect, it's one engineer. They found the tube system. That means kind of a perforated tube, right, made of concrete, kind of concrete grid, which creates a very strong structure for skyscrapers. And it was competitive of steel for about 30 floors or 35 floors. And again, this is a typology we still can see today. Of course, Le Corbusier was kind of an apostle or evangelist of concrete, both for its structural and for its plastic properties. And well, it went to Japan. Japan is becoming also very good. It was, I didn't bring it here, but in 1930s, Japanese were the first to build the full earthquake-proof buildings in concrete. Some of the old Japanese buildings we have in Seoul, like today's artist house in Haehwa or the School of Medicine, are this kind of concrete structures, right? Which is very, very innovative. It was like a very first ones. Le Corbusier was quite upset here because the Japanese were too precise and it lacked the roughness he liked, but still the building is there. John Utzon, as I mentioned, he's a Danish architect, or was, and he did many experiments. This was not built, the Langelinie Tower, but it's an amazing project which also explores those possibilities of concrete for very unique, unsuspected typologies of towers. I didn't put a date, but probably 1950 somewhat. Right. Felix Candela, Spanish engineer who went to Mexico and stayed there, did another of the milestones, not the only, but they tried to make this very thin concrete shells. And probably his masterpiece was a Barcardi plant in Mexico. It's 1959. We have 30 meters span, 12 meters height, and 40 millimeters, just 4 centimeters in the highest point. In the base is a bit thicker, right? It's like really the limit. And you can see from the photos, of course, the forming was very challenging, and the 1959 labor was not a problem, right? This is two things why we don't see those shells so often anymore. They are quite expensive to build. And the codes are so strict now that those 4 centimeters may be not enough for many issues, especially durability of the structure, but still not standing, and you can see it. He did many experiments, and the question was to be lighter, right, with the concrete, and he had to demonstrate the possibilities to convince people those structures were strong. And those possibilities, Eero Saarinen, I think Finnish, American, Finnish American, second generation, he used this concrete like creating a new language of architecture, going to this kind of, not the very engineering of Candela, which is a clear dome, but like this flying shape. And non-surprisingly, Saarinen was in the jury of this famous project, Sydney Opera House. Actually, this project was already discarded. Saarinen said, let's go back into it, and he was able to convince the jury to make this building. Utzon was thinking on using the shells that Candela proposed for the Opera House. It proved to be a challenge, and we are, see, 1957, this is time, late 50s was like the golden age of concrete exploration. But you see the time of construction, 16 years. Actually, the construction of that shell proved impossible for that shape, that size. And the engineers were 6 years trying to find a way to build this. And then it was not a shell, it was kind of a rib structure. Such a scandal that Utzon was fired. In the 1960s, 70s, people would fire architects. Now we just keep them and pay whatever is necessary. But it was very criticized, but yet it is still the icon of not only Sydney, but the whole Australia. But it marked a point in which that optimism of the 1950s, 60s of we are able to build anything went down, and architects became a little more realistic about what to do. And that feeling remained for 40, 50 years until 2000s, early 2000s with the Star Architect period. Still, 1950s, 60s brought this era of a more gentle use of concrete, still big spans and more plastic qualities. And this is 1967. The following year, Seoul responded to another big engineering project. This was the Seoul Country Club. Now it's the Kunmaru in the Children's Grand Park. We saw it also for, or didn't see it. No, we will see it probably later. But great structure, great construction, as good as anything done in the world at any time. 1960s, 70s was a very exciting period of Korean architecture. Again, 1960s, this is Spain. And this is a project in which the concrete was used in both its plastic and its structural possibilities. Again, very long project, but not as painful as that of Hudson. I go back to Spain. This is Fisac. He was kind of crazy about concrete. And he did many experiments, like using textile forms to create a very unusual, very surprising, puffy feeling in something which is very hard. This is something that today, the 2020s, it's been recovered as something very advanced. He did not only that, he went into many skeleton structures based on the structure of the bones, kind of hollow structures, or just very simple prefabrication in which very few units make a lot of variation. IBM building, this is about 0 and 1, 0, 1, right? This is the computer science. So he has only two positions of the facade elements, kind of the facade being the metaphor of the computer language. And he did more. So using like a very simple way of construction to create a very complex shape. This was very loved building in Madrid, but it was demolished 23 years ago. And the engineering part, not for aesthetics, but for the use, is also important. And probably Luis Kahn with the Commandant, which is his collaborator. Luis Kahn buildings look simple, but they have a lot of engineering there. The Virendel precast beams, which are like a one floor height complete, which allow to have all those systems in between the floors, and also have big spans one way. Nowadays, we are recovering, as we said, this kind of fluffy, soft forms to create unusual textures and light construction, different forms. We have Garcia Abril, we saw before, like more artistic, taking out of context, like oversized precast elements to create just a simple one-family house, or also taking precast elements out of context. And there's many more, right? There's many more possibilities, but things we do today probably are based on those basic things we see there. So let's go to the material. In that sequence, we saw today we will concentrate on the material, which is enough. Before I took this course, the person teaching before me used to have 10 weeks only on concrete. We'll have hopefully 1 hour. So please listen carefully. Let's go into the material itself. And this is the outline. We'll stop a little bit here. This is where we have a little bit of chemistry to understand the basics and something which is very important, right? Then we go into all the boring stuff, but it's important because knowing the nature of the concrete and how it is made allows you to understand better why we design it, which way, and the possibilities, the limitations the material has. We have to start with lime concrete. And you remember lime is that pure white stone, semi-diameter stone we saw, right? This is the lime, the concrete the Romans used. So you have to start from the limestone. And one way to essential is to burn, dehydrate one stone, make it powder, to rehydrate and create a new stone, but in the shape, the size we want. Furthermore, we add stones inside So we have a very much efficient use of that material because a small amount of lime produces a big amount of concrete. That's it. That's the powder plus the stones and the water, right? And that creates the concrete. This is like a archaeological remains of the Roman concrete. So let's say this is an artificial stone, man-made stone. Lime mortar, as we said, produced from limestone. And we know that limestone is produced by calcium carbonate. And this is interesting because it's a very easy to manipulate chemical. The process is as it, you can see, if you apply heat to calcium carbonate, you create carbon oxide, which is quicklime. It's very corrosive element, plus CO2. Yeah. Environmental people get panicked with this, but do not panic yet. So this is the first time we burn in an oven. The CO2 goes to the atmosphere. There's no way, but we have this kind of powder, which is the calcium oxide or quicklime. If we hydrate, if we add water, we had what we call the hydrated lime, right? And it releases a huge amount of heat, which also have to be into account. So it's a chemical reaction in which we start to reconstitute the element. But it's not yet the same material, right? We need still the carbon. That carbon comes from the atmosphere. So actually, we are capturing carbon. So, and this is the process of hardening. This is why it takes time. This is a slow reaction. So with the absorption of the carbon dioxide from the atmosphere, we have, again, the calcium carbonate. And this is a process which could be repeated over and over. Apparently, if you repeat over and over, the material degrades a little bit, but the chemistry is so simple that it's very easy to replicate. Right? This is why metals, I get off topic, but are so easy to recycle. The chemistry is just the atoms together, right? So it is very easy to recycle because it's nothing to degrade. And this is why plastics are so difficult. The chemistry is so complex, those molecules get wrong very easily. Okay, so the summary is what you see here, right? We just destroy stone, make it powder. By adding water, we recreate that stone again in the shape we want. And we add just the sand, gravel, and stones, we have the concrete. So the concrete is that kind of a powder, that kind of glue, right? With the addition of the material, which makes necessary to use a small amount of that glue, that powder, to have a big amount of new stone. If you understand this, this is a small video just for you to see, if you didn't experiment it, how much heat it releases, right? So those small amounts make the water boil in seconds. Those who did the military training may have studied how to use lime powder just to heat the food without producing smoke, right? So this is boiling. And this is why quickly lime is so efficient to hide dead bodies. They disappear. Okay. So be very careful with the quicklime. We seldom use it. Portland concrete has much more complex chemistry. Not the concrete, the cement, right? So to this we use the Portland cement, not the lime. And this is just made of a limestone as a base, but clays, silica, and other materials which create this kind of gray powder we know. And that was discovered that's much harder than the old limestone and much more durable, right? So we have the lime, the clays, we burn it, we grind it, then we add other materials. We have what we call the cement, which is the basic glue for today's concrete. And then we'll add, as usual, the sand, the gravel, the stones to make use of it. Something I put as a note is very side, but alumina is one of the additions people were very happy to put. Remember, alumina makes it stronger against fire, so still we use it. But alumina has a very nasty performance over time, and it can corrode the reinforcements, right, with other chemicals. And it was very used in the 1960s and 50s, up to the 70s, because it was very fast. One problem of the concrete, it takes like 1 month for it to harden to a safe stage, right? But alumina could do it much faster. So it was very popular. We are much more careful now. I say that because if you work in old buildings, renovation is very common, and we have plenty of those. Probably Korea was using it until the 80s, even later, right? Because here things become a bit later because of the development. Always be careful and test the nature of the reinforced concrete use and you use and to see if they have any kind of damage, right? We do as a base when we work in Europe or America in buildings from that period. So the fabrication process is, I will go fast here because not much to understand. We quarry the clays and the lime, we grind them, we burn them, we grind again, we mix with the materials, we have the powder ready for working. So we take, we couldn't sit in the bricks, but this is clay, right? Clay is like a real sedimentary rock, and you need the dynamite to get it there, to start using it. That creates those rocks which are transported, right, for then grinding them, mixing and making the powder. So once you have them, they are stored in this process of grinding, storing, and then they will be mixed, right?
There's a constant spray of water to keep the dust from billowing up and settling on the chutes.
Fortunately, there's not sound because it's really noisy part of the process. So very thin grounding. It's not yet at the final grinding, but then it is transported and stored because different kinds of cement will use different mixes of clays, as we saw with bricks, but in this case, it's even more exaggerated. So once they are stored, they are mixed in the proportion necessary for the given kind of cement which we want to fabricate. Right. And this is other, like pure silica and other materials which are added to the mix. Right. Well, and then it is all burnt together in a very strong, huge oven, right? Which is rotating. It's like huge tube in which things move slowly, right? And are mixed. And the temperature you see, it is enormous, much higher than the one we saw in bricks. That means the amount of energy we use is much bigger. And those huge tubes are the typical ovens. This is where the gas with the fire goes, right? Those are typical of the cement production. What goes out is something we call clinker. And be careful because we call clinker that very high temperature brick, and we call clinker the burnt result of the cement production, but it's two different materials. Right? This is very finely crushed in that thin powder we know, and then still has a bit more additions, right? So gypsum and other materials to stabilize those very complex, much more complex chemical reactions, so the material performs as we like. Okay, so now we have that powder, that gray powder we all know. This is like the basic glue, but then we have to add the water and the other materials to create it. In small constructions, still, and developing world, still they do by hand, but mostly today, especially for structural concrete, we do in a factory because we need much careful result and good quality of the material. Basic components are water first. I will not speak more about water because although it is one of the chemical elements we are more ignorant, we still don't understand it. It is well known, whatever. What's important of water, it must be pure, without salts and without sulfurs. So we need always to analyze the water used in concrete. In the factories, they have very careful system for monitoring and checking the chemistry of the water as neutral as pure as possible. And of course, we know water is the element which creates a chemical reaction. It's part of the concrete, the cement hardening. Then what we call the coarse aggregates, sand, gravel, sometimes stones, not so much stones because in structure, we don't really want them. It's what makes us safe, use as minimum quantity as possible of that very precious, very expensive cement, right? And we will comment later, cement, right? Portland cement or just Portland, which is the glue. We have plenty of different cements. Fortunately, the concrete factory will take care of it, but you have to be aware of it. And then not the chemicals we add to the cement, but some chemicals, some other elements are added often to that concrete mixture, right? And there are plenty of them. And in English, they have admixtures, which are reactive, and additives, but that's kind of linguistic thing. And there is infinity of those. Mill aggregates, mostly sand. Best is river sand. Otherwise, we have to wash it, especially sand from the sea, right? Because salts. And it must be free of clay. Clay particles are like less than, say, 1 or 2 micrometers, right? Like a 1,001 millimeter, 1,001 millimeter. So that fine particles we try to avoid at all costs. Why? Well, if you did pastry, you add the powder just to avoid things to stick, right? You have flour. So that fine powder will prevent the cement to stick to the stones, right? Will prevent all that action. So we need a sand, thin sand, but we have to limit those things. And then I will explain this, but I want you to keep your weights, and this is a way of doing it. After the sand, we put the gravel. That's small pebbles. They can be round, they can be crushed. So it can be rounded, polygonal, and they have to be graded. So how the mix of sizes may affect the result of the concrete? What effect they may have? We may have all the same size as in the photo. We may have different sizes. They might be rounded. They might be polygonal. How do you think that may affect to the final result? Thinking that this is just a filler, something we fill to use less cement, right? Which is the expensive part. Do you understand the question? So I put those stones. They can be rounded, like taken from the rivers, or can be crushed, like quarries and so on. What happens if we use one instead of the other? If we use different sizes or the same size of it? Just think about it, because I will explain now, but if you think about it, then it's much easier to understand, and then you'll remember for the exam or for the quiz, for both. 2 minutes for this. You can speak, you can draw, you can write. Drawing usually makes easier to understand because you make the diagram of the rounded or the polygonal and the different sizes, and you may see how this affects to the total amount of each material used. Okay, time to write something. If you have no idea, it's perfectly okay. Just draw the 2 diagrams. So you demonstrate you were here, you were looking at the screen, so you know what this is about. Good. Now we have to put energy to this thing here. Okay, so let's go into it. So the aggregates can be on many ways. And the important thing is first the size. Usually we use like a maximum 2 centimeters, sometimes 3 centimeters, but if we have a reinforced concrete, especially we don't want to use very big stones. Your activity sheet, you have already? You? And of course, we need hard, compact, regular stones. This is why curiously granite is not so good because it has this kind of small sheets of mica which do not help, right? So rounded elements will provide more compactness, so you will have less cement to be more economical in that sense. It's preferred, but angular ones will have more area of contact, so the adherence will be better. So there is always a trade-off there. They are both okay. Of course, if you wash the concrete, they have a different aspect, right? The other thing is the grading. This is important. And actually, all those days, they would spend like 2 weeks studying all the formulas of grading the coarse materials. You have the percentage, right, of each diameter. This is the diameter of each of the particles there. You see, we try to have almost nothing of 1/10 of a millimeter, those small particles, and we try not to go over 3 centimeters. And this is kind of the ideal curve. You can go with a larger margin, but the idea is to have all sizes in a given proportion. It is different with the crushed material and with random material, but that perfect grading will give you much better complexity. If we have only one size of gravel, you will use a lot of cement. If the grading is not very well done, you will still have a lot of gaps. So all the science of the grading is to have as much complexity as possible. So good grading will have less cement, will be more economical, but we have also much more area of contact. So the cohesion will be also stronger. This is why grading is so important. Admixtures, and this is a difference between admixtures and additives. It's mostly for English. I don't know about other languages. Admixtures are chemicals or other materials you add to the concrete which affect the chemical reaction. Right? Or the most important and the most used is the plasticizers, which makes the mix of concrete to be able to work, but without falling apart, right? So enough to go to the form and take the shape, but without being too fluid or too hard. This is like almost universal. Then you have something to make it harden later. You have something to make it more thick. Imagine you have those shells or something in which you don't want the fluid to pour around. You have accelerators, sponges to create a porosity and so on. There's plenty of those. This is the most important. Well, I took a Sika in Swiss, one of the biggest makers. They have like a catalog of dozens of those materials. Then additives usually do not change the chemistry or do not interact with the material itself. And usually colorants or fibers, sometimes instead of reinforcement bars, still we use fibers, right? Or puzzolanic, we will see later. I would put it in admixtures, but okay. It's kind of a powder, which is interesting in the final result, right, of the concrete. The dosage is different from grading. Grading is just for finding the size, the proportion of those sizes of gravels and sand. The dosage is how much we put of each material. Remember, in mortar, we spoke only of sand and mortar. Water is mostly by filling. In this case, we have water, cement, sand, and gravel. And here the proportions are vital. because we're speaking of very delicate structural material, we want to be sure of the material we are fabricating. There are many ways to do the dosage. Usually we do by weight. We will not go into much detail. You don't need to memorize things, but it is good you are aware of the ranges, the usual ranges for the usual concrete. So usually for the normal concrete, I'm speaking of the everyday concrete, not the high strength concrete, which is very specialized. Cement usually is 250 to 400 kilograms per cubic meter. Less than that will be weak. Over that, still we can use, but it will be much harder to control the reaction, the cracking, the heat, and all that. We go almost to the high strength concrete, which is probably 800 kilos or 1 ton. So this is the most common range of the everyday concrete. Aggregates, which is sand and gravel, about 2 tons, right? By far the most, as we said, right? We want to use as little as possible as cement to have the result. And then water can change this about 150. That's a very small amount, but it's important. Less water and the reaction doesn't complete. More water and you have too fluid material and will not have the result we want. The differences are very clear, right? And it is good you're aware of that, because sometimes you can spot errors, especially when the concrete is done on site. It will not happen in a factory, but if you're in a developing country, cooperating or something in some country in which they do on site, at least you should be aware of the main numbers, right? Just the range. Remember that stone is about 2.5 tons per cubic meter, and altogether make this kind of total weight, right? Which is also one checkpoint. Once we have the mix of the concrete, usually goes with a truck, yeah, the Remicon, and usually the time limit is 2 hours. So very important, you have the certificate of the time getting out and when you pour it. If it is late, it has to be disposed, which is a problem because once you dispose, it hardens, it's very hard to clean. So when you have a construction site, especially in big towns, it's always a challenge to be in time. This is why you have still concrete factories within the city of Seoul. Then about the properties. As we said, the density is like the usual stone. It's basically limestone with gravel and sand. The variation will be mostly by the kind of sand or gravel we use, because the stones can change in density. Compression, the usual strength, the usual concrete is between 100 and 500 kilograms per square centimeter. For reinforcements, minimum is 175. But nowadays, I think the Eurocode in Europe, they consider only concrete over 250 kilograms per square centimeter. Okay, I don't know the standard of Korea, but about 200, 250 is like the usual for most common everyday concrete. And then the high strength goes much, much higher, right? There is a space between 500 and 800, it's ambiguous area. If you go to the pain of add a lot of cement, you go to much more strength, because you will need always special laboratory work and really specialized workers. And this is what you see in the columns of high-rise towers of 50, 60 floors. Because with this strength, it becomes competitive with steel. But this is very specialized, right? And I personally have seen it, but I have never used it. But I have an idea of the problems there. One thing we do always when the concrete arrives to the site, to be if it's okay, we have the slump test. It's kind of a conic form. It is poured, it's like a pudding, right? And the workers check how much it goes down. This is the ideal consistency we want, to be soft, but still to keep it all together. So we know it's a good quality, the concrete we need. If it is totally rigid, it will be hard to fill the forms and to work. And it collapses or have shear. Probably the consistency is too soft and it will have problems when it hardens. Other thing which is done in structures is the statistical test. Usually for every truck coming to the construction, about, depending on the strength of the concrete and the safety regulations, between 6 to 10 samples are taken for each truck coming, and they are taken to the laboratory, perfectly prepared, and they are broken 7 and 28 days later, right? 28 days gives us the intended strength. 7 days lets us know if there's some kind of problem. We can just check ahead, right? But see that 28 days is the standard time for the concrete to be hard. 1 week already is strong, but it's not its full resistance, right? And then it is broken. The laboratory makes the calculations, and they send it to the engineers, architects, and you see if that works. And of course, if we use like a 250, it is never 250, right? Usually it will be a bit more. Seldom it is less, but if it is less, you have to make additional tests. Okay, then we have the reinforcement, because you can use concrete as a mass often, but we put reinforcement, and probably you already know concrete is very strong in compression, but very weak in tension. Still, it has some strength. So the strength is about 1/10. We usually do not use in calculation, but it's additional safety we have. So if we compress, say, one column may collapse with 200 tons of weight, usually because of the shortening, actually this will be fattening in the center, right? Shortening, fattening a little bit. So little we cannot see it. This is why the cracks are vertical. Very important. Vertical cracks parallel in the center of the column. Memorize it, visualize it, put in your mind, because you have to be aware of it. Not only because it comes in the exam, because many collapses came for ignoring this, okay? Whereas in tension, it will shorten in the middle and cracks will be horizontal, perpendicular to tension area. So to have a more versatile material, we put steel reinforcements. And this is something you all know, so I will not explain, right? Steel and concrete work well together. Water in concrete is an annoyance because water oxidizes the steel. But since the water goes to the concrete for the chemical reaction, it's kind of safe. And the expansion, the heat expansion is not the same, but it is quite tolerable. They can just expand and contract together. So it's kind of dream combination that engineers started to test like 100 and somewhat years ago, right? And this is what we call reinforced concrete, or RC. The use of steel to absorb those kind of tension stresses. Another thing is that the concrete is recovering the whole steel bars, so concrete will protect it against corrosion. So let's go to the rebars. We don't need to speak too much because we already are experts on steel. So this is a mild steel, and rebars has some kind of a texture. You see they oxidize a little bit. There is opinions about this. Steel should be clear, but a little bit of oxide, usually people do not care much about it. A lot of it you will have to clean, but ideally you use them clean, okay? So usually corrugated is this kind of texture bars, this kind of, so those kind of texture, we call it corrugated, yeah. That's the texture of those bars. This will help having more connection, more adherence to the cement, and usually between 6 and 25 millimeters. If you have a pre-welded nets, you can use thinner, like a 3-4 millimeters is also very common, right? And over 25 millimeters, they are so heavy and so hard to work that you will see them mostly in civil engineering. Actually, 25 millimeters are never used, very seldom. And 30, 35, and 40 millimeters, you will see in bridges, in big domes, in in nuclear reactors and things like that. And the strength, we're on the high side. Between 4,000 and 6,000 is the most common, right? We said since the material is very small, it's very easy to control the strength. So we'll have always higher strengths in small bars than in big hot formed shapes, right? So it's probably the strongest steel you can use. One thing which is interesting is, please remember, mild steel has the same strength in compression and in tension. Don't say steel is weak in compression, because you will fail a quick exam, which is very easy, right? So if you have a concrete and steel together, if they're compressed, they will both shrink together and the steel will be pushing together with the concrete. If they are in tension, we just neglect the concrete and we consider only the steel is working in tension. But in compression, both have a column with reinforcements. If it is compressed, right, both steel and concrete are shortened and they are both pushing, collaborating. And this is why you put bars in compression, and this is why we use them also in columns. But curiously, in compression, we go usually to the minimum value, only 4,000. We can use a bigger steel or stronger steel, but we calculate only 4,000. This is why we reserve those very expensive steels only for beams or elements which are in tension. And this comes to the question, and this is a difficult question. If you are able to reply to this, you know more than some of your colleague engineers. Why is that limitation in compression? Why, if we use a 6,000 or 6 Pascal steel bar in compression, we will calculate only 400 megapascals when it is in the reinforced concrete? Can you think of any reason? I gave you a hint with the diagram before, and surely here Young modulus may help you. This is a nice exercise to elaborate on what we commented the other day, but if it is beyond your understanding, don't worry, you can survive without it. But it will help you much understand about elasticity and the performance of materials and why many things are done in the way they are done. And understanding things is always good. Any idea why? I will explain next week with the questions and answers. Remember that in compression, this element will shorten, and both concrete and steel will shorten together, the same amount. This is just a by need, right? They have to go together. So if the column becomes 3 millimeters shorter, both concrete and steel are shortened 3 millimeters. Well, as usual, comment whatever you think is possible. Otherwise, just copy the diagram so at least you have the image in your head, because the point, the tip or the reason is this diagram, this kind of joint deformation. Good. Let's continue. So reinforcement, again, needs to be protected against oxidation. So usually the thicker is, if we have one section, you're familiar, right? The beam or the column with the reinforcements, the thicker is the recovering, the better is the protection. In general, at least 3 centimeters, 2 to 3 centimeters is what we consider. In very aggressive environments, you can go up to 10 centimeters. But if you have a lot of distance, that's a very thick part of concrete without steel. So you may need additional secondary thin steel to avoid cracking there. Of course, thicker bars will oxidize less. They have less area in contact with the corrosive agents. And if the concrete is stronger and more compacted, it will give more protection. So 300 kilograms per square centimeter, or say 30 megapascals concrete will protect better than 20 megapascal concrete, right? And finally, if we have very rich clients, stainless rebars are fantastic. I have the stainless steel industry trying to sell me, but I never found a client wanting to use them. But still, they may have their place. The adherence, you know, concrete is like or cement is like a glue; it sticks. But you want to be sure that connection is as good as possible. So the corrugation, right, this kind of texture of the bar, is what allows to have bigger strength. And the patterns usually have encoding the resistance. So in Europe, this will be like a 40 megapascal. This will be like a 50 megapascal steel, just by the shape. In Korea, the states have different ways of doing it, but just by watching the pattern, we know which steel we are using, which is important thing, because as we said, we may have different steels in columns as we have in beams. This is an example in Korea, 22 millimeters, 50 megapascal concrete in columns. But we know that in compression, we will never use more than 40. Okay, and as possible, clean, small stains of oxide is not usually a worry, but we have not used them very oxidized. So I will show you just a fast slideshow to see how this works on site. This is the construction of this building. Okay, so you know how this inside. The reinforcement horizontal is done by hand. Usually the bars come, they are cut, and they are placed by hand according to the construction drawings. Same for the vertical. Usually they are cut and placed by hand with just small steel wires. So it's very, very artisanal. Sometimes they prefabricate and you have like the full set of steel. This is done also, but in Korea, I see always doing it by hand. If it is not flat, like a vertical or horizontal, you need some form to bend those steels. This is from the DDP construction for this kind of wobbly concrete buildings we have in the perimeter. As we saw with the steel, we have some kind of a basic pre-dimensioning for your projects. You have some kind of realistic section. This is for slabs. For beams, it will be a bit more high, like probably 30, 40% more. And you see, this is kind of exponential, right? The wider the span, the higher element we need. But this is taken from the book of the Plazes. In general, as we said, 1/20 of the span of the height will be worth in average spans, like 5 to 10 meters, like the usual construction. So in 10 meters, you will have 50 centimeters slab. This is solid slab, which is very thick. This is why you never use solid slabs for big spans, right? If you go like a larger, say 15 meters, you need much more. Those slabs are used mostly in civil engineering, in bridges and things which need a lot of strength, not in buildings. But you know, probably one beam would be like for 15 meters, probably 1.5 meters thick, so it's very big, unless you use a post-tension or pre-tension, which is a little bit beyond what we have here. And for the smaller spans, you can go to 1/30th. So the difference with steel is not very big, right? Right. Still, you can be a bit more conservative, but still, the 1/20, 1/25 is like a very universal way of dimensioning for normal spans. This is what we see in Seoul. So most common is to have a very close together beams, so the load is reduced, so you have longer spans, right? With very thin slab. So this slab in between, so you have like a 3 meters, maybe 15, 20 centimeters, very thin slab. So the structure is kind of efficient. For spans between 6 and 12 meters, a waffle slab is great. It's the one we use mostly in Europe since 1960 or so on. 1960 because it is hard to calculate, right? Here in Korea, after the Sampung Baekwacheon disaster, which was a flat slab, People have allergy to the system, but it is great. You can have a really light structure, and it was perfect. Formwork, we said the concrete is poured, and we need to give a form. So formwork is important part of the process. I show again this construction. This building has rectangular columns and rectangular beams. So this is made by carpenters. This is a timber chipboard or fiberboard with a plastic melamine interior, so the cement does not stick much and has very nice clear finish. And those are created on site, right? It's like a really boxes. Once they're created, they are put in their place, right? And then the elements, this is, we'll see later, the form for the thin slab in between is created. This element is very common also in Korea. It's about 3 meters, 4 meters, and they have already some reinforcement there. So it makes very fast, very easy construction, and they become part of the structure. This is like a lost form, right? And since this is steel, it already is working in tension. So it's quite interesting material. This is how it is ready for adding the reinforcement. You see here, the steel is just a plane, and people just transport it. And you see, it's like very primitive. It looks like a Roman construction, right? And steel is very heavy. So those guys can bring like 2 or 3 bars at a time. And they are put in the proper place. So you complete the full beams, right? These boxes are just to make a hole for the pipes, the ducts for the systems, right? And this is an opening for the stair. So in that case, you see the 15 centimeters thin slab, because this is a very small span, but still you have a lot of pipes inside and the reinforcement waiting for it to be closed later. This is where the crane, the tower of the crane stays. So it has to be closed later. Stairs are a complication always. It's a good idea you make in concrete, because you have as soon as the concrete is hard, you can use them. But during construction, it's kind of a small nightmare. This is like one of the most difficult parts in the construction, and where more errors. We have them always wrong in the sections, in the drawings. No wonder we have even more errors on site. This is already the structure with all the reinforcements ready, working around the clock. Those colors are the electricity and the piping. Now we have so many systems, and we try to avoid it, because we have areas of concrete which are totally hollow, and this is not calculated. But this is how we do things in Korea, right? In most places, we'll put cables outside of the slab, which is much better, or you will do in a way you can calculate that loss of material. This is the pump arm for the concrete. Remember that those forms are risky. Even that small stair always needs a lot of engineering, because concrete is very heavy, right? And this fluffy. So if it collapses with tons of concrete, we can solidify. So as you know, with the accident we had this winter in Gwangju, right? That kind of a concrete just collapsing with the support made very difficult all the operations of repairing, salvaging, and so on. So it's very critical. And those collapses are not only Gwangju, right? This is Spain, and this is Calatrava, which is a top architect, top engineer, top construction company. The form collapsed. Fortunately, there were not big casualties that I know, but just the repair in one was like a Texas ship up, which is a lot of money. So forms are tricky. Make sure the engineers work on them carefully, right? And they're not removed until the concrete is hard. So the rebars need to have some distance to the form, otherwise they will corrode. This is why I put separations or spacers, usually cement or plastic. Plastic, we try to make them as small as possible so we do not lose mass of concrete. And then once we have ready, we pour, we compact. Pour, compact, and then level. That's the process. Compacting is usually done by a huge vibration machine. So you see you have a lot of movement. You have the pouring of the concrete, the vibration. So this creates a lot of stress to the form, throughout the professional structure. You have a lot of people working there. So you pour, you compact, and then you level by hand. And now you see this is all done by the eye, right? They are very skillful people, but tell me, how can you control the slab being 1 or 2 millimeters thicker or thinner? This making the measures in millimeters has no sense at all. This is more or less the thickness we proposed. So one last question, and here we have time because we have still 8 minutes of class. And this is just for you to do something, right? What happens if we compact too little? And what happens if we compact too much? That's to tell you that it's important to compact the exact amount. Otherwise, you will spoil the concrete. And this is why that compacting is important, but it's also very specialized. And it's done just by the feeling of the guy doing it. So you see, reinforced concrete is very artisanal. It's very primitive in the end. Okay, I put 2 minutes, but we are short on time, so let's have only 1 minute. We are almost ended. And I will tell now, but I want you to figure out, try to guess. Okay, did you write something? It's okay, you copy what I say later. Important is that you get the idea, right? So if you compact too little, you have plenty of bubbles in between. Remember that the concrete is very thick liquid. You have a lot of reinforcement. So you have to be sure that it fills all the gaps. And the poor compacting creates very poor concrete. Not only will create oxidation in the rebars, that section will not have the strength we calculated. So usually it should be demolished and rebuilt. Or if it's not too bad, repaired. But repairs are always bad. If you compact too much, may happen. It happens often in columns. Very difficult to compact because you have to go very deep, right? If you compact too much, you will break the mixture. So you may have all the heavy materials, the gravel on the bottom and the water going to the top. So the mix is broken. If you do pastry, you know what happens when you overmix, right? This is kind of pastry at a big scale. So this is why the compacting is very specialized and very important. You have to have people who really know what they are doing. Shotcrete is a special case. It's like a very high pressure, just shot to the walls. It is very used in swimming pools and civil engineering walls because you avoid one form. Actually, it's very compact. Doesn't need compacting. It's very resistant, but it's also very tricky to apply. So it's nice you know about it. Once we have it perfectly done, we need the curing. This is extremely important because we know the water is necessary for the chemical reaction which makes the cement harden, right, to have the whole mix. So and that curing lasts for the 28 days, it's a full month. So people in charge of the construction have to be sure the concrete is not dehydrated, but there's not too much water either. This is the construction here. You see, as soon as they put the concrete, they put the vinyl on top of it. It's polyethylene, so the humidity will not be lost. This was a period with some rain. You don't want also to have water from the rain, not only for the pollution added, but because it will change the proportion of the materials, right? So you have to be careful about it. You see the guys leveling by hand. And this is how it is done. This is everything prepared. And I have two small clips. Let's see if they work, because you see how if they work, because they have to. Didn't work. Let's see if this goes on. Well, they didn't work. but you have them in the links if you want to see them. You can see the real life process of this kind of pouring and compacting and so on. Then something that happens in the concrete, in general, it shrinks when it hardens. And something we have to consider. This is one of the exposed concrete in DDP. It cracked everywhere and people were in panic. They rendered it and it cracked again. So it's something we have to be aware, right? One thing we do, of course, reinforcement will help controlling those cracks. In very long elements, we usually put grooves, right? So the crack will be more or less when the groove is, if we are lucky, right? This is by experience, and otherwise you will have just the reduction cracks and you have to live with them. In floors, for example, people will cut off this harden, it's like a 3 by 3 or 4 by 4 meters. So, and still it can crack, right? But still, or you may put, well, this is the ratio, put flexible joints. So you have very small bits of concrete. So the effect of retraction and expansion later will not be so much visible. And the cracks are natural. We try to avoid them by being more careful with the reinforcements or with the additional fibers, but it's always annoying, right? And there was like those cracks appearing always in the news, probably were just due to the nature of the concrete material, not really being pathological, not being a problem of the structure. To being able to distinguish between both is important, but it's a little bit beyond our course. If you go to the book has a bit more detailed tips on how to produce concrete. You will see it in the handout. You can read it if you want. And exposed concrete, as it is poured, we can give a texture with the form. We are used to see it, or we can apply the same treatment we apply to the stones. So you can have sandblasting, push hammering, chiseling. Probably can even flame it, but on site is a little bit difficult, right? And it's a bit aggressive. And well, this is kind of from the book, also a listing of the finishings you have. And then we have special concretes, which I will just list because some of them are very used, some of them as kind of curiosities. Hemp concrete is just adding vegetal fibers, hemp, to the mix instead of steel. That's used for the small light concrete bricks, right? They are insulating. Translucent concrete was a hype a few years ago. It has like a optical fiber lines inside, so you can see the light through. It's quite interesting. It's got thin elements of concrete that are cut to have this kind of transparency. Colored concrete is very common, right? And I put yellow because I always wanted to have a yellow concrete, and apparently it's very expensive. So depending on the color, just added colorants. Of course, changing the gravel type can have also an effect in the final color of the concrete, right? Light concrete, instead of gravel, you use like a light elements. Usually it's expanded clay, things like that. Mostly used in bricks or light concrete for roofs. And fiber reinforced concrete is interesting because it is very hard. So the fibers in that thick element are very hard to mix, right? But if you have it, you can avoid to have the reinforcement bars, and you can have much thinner, much lighter concrete because the steel adds quite a lot of weight. You have this kind of mostly prefabricated elements, light construction with usually fiberglass, nylon, even steel, but steel again will corrode because some of those steel bits will appear in the surface. Terrazzo is like a very specific way, very thin plate of cement with very well chosen elements of gravel, right? And then it's polished to have all these textures we have around. We have many of those. It's done on site or in factory with tiles, right? We have old buildings around the campus all have this kind of, you will see in the stairs, in corridors, and so on. And what we call hydraulic tiles, it is the same, but instead of using the gravel, they use just a powder of cement with different colors. and then they are hardened and polished. This was a very cheap kind of pavement. Now it became kind of a vintage and very priced, very much sought after because they're interesting. But it used to be cheap. Now it has a lot of hand labor. Now they are very expensive, which is also interesting. And with that, we have there's many more. We cannot go into it. So many interesting things going there. And I don't want to go beyond the time. We are already 2 minutes beyond. Environmental issues, you can read. I will explain only one thing, which is important. So, you know, pollution and all those things, health. Of course, the fat added to the forms to be able to separate them, also polluting. About energy, we are in the limit of high energy. And durability, the secret for durability is good detailing, good engineering, right? If it is not well detailed and maintained, we have those kind of collapses, like a Florida collapse last year. It was bad engineering, bad maintenance, and bad everything. Shouldn't have happened. And just one addition is that vertical cracks in the columns. Be very aware of them. In 1970, this was a building 10 floors apartment by one of the professors in my school, right? I went to school in 1979, so it was quite recent in the memory of everybody. And he was the guy who wrote the book of concrete, right? So he knew a lot. So he saw the vertical cracks and he said, okay, I have to reinforce with the additional elements. But before they could do anything, it collapsed. And 15 people died. Doug went to jail. He had a very strong sense of responsibility. So he died just a bit later. In the end, it was discovered that the cement maker had saved money by adding too much lime to the mix. So the hardening was much slower than the usual. But the point, well, it was a very painful thing, those vertical cracks. So this kind of retraction tracks are okay, but cracks in the column are serious, especially when they are clear, they're persistent, and they appear there, right? So don't forget them. Then about recycling, you can read perfectly. There's not anything you have to see, only the pozzolanic thing. Pozzolanic is kind of a volcanic ash that the Romans used in their mixes because they saw that the concrete was very strong even inside the sea. So they used for the harbors and so on. Very similar are fly ashes, which is dust. This is a waste from the production of steel. But fly ashes have many kinds. If we add a small proportion, as much as 40% of the cement by fly ashes, by good quality ones, we have very strong cement, right? And we save a lot of material. This is regulated because it may help you, or we may make a disaster of concrete. Waste is waste anyhow. This is very regulated, but you have to be aware of it because it is repeated all over, right? Usually you don't have to worry because the concrete companies already have their own regulations and they inform you if they have it, okay? And that's it. I think we're in the end. So again, thank you so much for enduring the 5 minutes, but we saved like 10 weeks of concrete with this one single lecture. So if you have any question, please write it and be so kind to return all your sheets. And see you on Friday.